To be more quantitative of what happens near a fixed point, it's helpful to do a local analysis near the fixed point itself. And it turns out there's two generic cases to consider. The first case is when the function f of x has a non-zero derivative at the fixed point. That means that we come through zero with a non-zero slope, so that corresponded to linearly stable or linearly unstable fixed points. And here the analysis of what happens locally near the fixed point is very simple. So given x dot is equal to f of x, what we're interested in is what is the dynamics very close to the fixed point. So to figure out what's happening near the fixed point, let us take x is equal to the fixed point value x star plus some small deviation epsilon. Let's plug that into both sides of the equation and look locally for small epsilon. So on the left-hand side of the equation, when I take x dot, well, x star is the fixed point, so it doesn't change with time, and we only have epsilon dot. And on the right-hand side, we have f of x star plus epsilon, and we can now perform a Taylor series expansion and write this as approximately equal to f of x star plus epsilon and df by dx evaluated at x star plus higher order terms. And in the limit where epsilon is very small, we're going to neglect these higher order terms. And by construction, the definition of the fixed point is that f is equal to 0 at x star, the fixed point. So the first order term, or the zeroth order term, is equal to 0, and we're just left with the first order term, epsilon, and I'll write this as f prime of x star, shorthand notation. And I'll define this thing to be lambda times epsilon. So lambda is the first derivative. But this equation is very simple to solve, and there are two types of solutions that can occur. So epsilon of t, in the long time limit, this scales as e to the lambda t. And so there are two basic types of behavior. If lambda is positive, which meant that the function f of x went through the origin with positive slope, we have exponential repulsion from the fixed point. On the other hand, if lambda is less than 0, then we have exponential convergence to the fixed point. And in particular, what exponential convergence means, that the deviation from the fixed point goes like e to the minus lambda t. And what that means in particular is that the fixed point is reached in finite time.